Day 24.
Okay, they're asking is 6, for part A, is 6 a solution to this? Well, let's try. We're going to have the square root of 3x, which is 18, plus 18. Is this equal to x, which is 6? Well, this is the square root of 36. Is this equal to 6? Yes. So part A is a yes. Let's do part B. Well, I can see right before even doing anything, this is not going to work because a square root cannot be negative, and this is a negative 3. We can do the work if you want, but it's a waste of time. I know this is going to be no, this is not a solution, because the square root of negative 9 plus 18, is this equal to negative 3? Well, the square root of 9 is not equal to negative 3, so this is a no. The square root can never be negative. Okay, to solve this problem, we're going to square each side, and we're going to square the left and get x minus 2. When we square the right, we get 9. So when we solve this, we're going to have x, oops, what did I just do? X is equal to 11. Now, when you have a radical in the beginning, you should probably check to see that this is not what's called an extraneous root. I'll explain a little bit more about what that is as we go on. But 11 minus 2 is equal to 9. Is this equal to 3? Yes, it is. So this is the answer, and that's not an extraneous root. An extraneous root comes from the fact that if you do a squaring, you could possibly turn a false statement into a true statement. And then when you solve this, this could possibly come from a false statement. Let me give you an example. Let's say I started with a negative 5 is equal to 5. That's a false statement. But if I were to square each side, I would get 25 is equal to 25. And that's a true statement. So any solutions that come from this true statement are going to be invalid when applied to the original statement. Those solutions that came from this statement that do not apply to the original are called extraneous solutions. I'm going to try to spell that word. Extraneous. Those are solutions that work from this point after the squaring, but don't work in the original, and they have to be thrown out. Okay, I'm going to square both sides, and I'll get 6x minus 1. I'll square the right, and I'll get 1. I'll add 1 to each side, and 6x equals 2. I'll divide by 6, and I'll get x equals 2 over 6, or x is equal to 1/3. I'm actually not going to bother to check this for extraneous roots, because the square root here was clearly not a negative, so squaring that will not create an extraneous root. Okay, the first thing I want to do in solving these problems is isolate the radical by moving my 1 over. So I have the square root of 4x plus 3 is equal to negative 1. Now I'm going to stop and I'm going to say no solution, because a square root cannot be negative. If you were not careful and you squared each side, you would have 4x plus 3 is equal to a positive 1, and this would yield a result. But that result is not going to work in the original equation. It's only going to work from this equation, and so that would have to be thrown out. But save yourself the time. When you see that you have a square root is negative, just stop right there and put no solution. We're going to start by isolating the radical by moving this over, and we'll get the square root of 3k plus 1 is equal to positive 4. Now we can continue because our square root is positive. So this is not going to create an extraneous root. So I square the left and I get 3k plus 1. I square the right and I get 16. I subtract 1 from each side and get 15. So k is equal to 5. Now you can check this if you want. As long as you did this work correctly, this check is going to work out. We know it's not going to be extraneous because it came from a place where the square root was clearly equal to a positive. Okay, I'm going to start by isolating the radical. This time I'm going to move this one over. So I have 4 is equal to a positive x minus 2. Now, This is a square root that's equal to a positive, so I'm going to continue. I'll square each side. I'll get 16 on the left and x minus 2 on the right, and then I'll add 2 to each side, so x will be equal to 18. You can check this if you want, but I know it's not going to be extraneous because it came from an equation where the square root was clearly a positive number. Okay, here we have a radical equals a radical. When we're done, we should probably check that our solution cannot make either of these radicals, oops, what did I just do? Either of these radicals equal to a negative number. So let's do this. I'm going to square the left and I'll get 9a minus 4. I'll square the right and I'll get 8a plus 1. And I'll move the 8a over and I'll get a. I'll move the 4 over by adding it and I'll get 5. So a is equal to 5. Now I should probably check that. The square root of 9a is 45 minus 4. Is this really equal to the square root of 8a, which is 40, plus 1? Well, that tells us the square root of 41 equals 41. That works. So I know 5 is a valid answer. Okay, so I'm going to start by squaring each side. When I square this, I square the 2. And when I square this, I get x. When I square the right-hand side, I have 3x plus 4. I'm going to bring the 3x over to the left by subtracting, and I'll get x is equal to 4. And so now I should probably check to see that it's not extraneous. Actually, I can see that it's not, but let's do this anyway. This 3x is 12 plus 4. We have 2 times 2. Is this really equal to the square root of 16? Yes, that's true. So that's the solution. Okay, so I'm going to start by squaring both sides. When I square the 3, I get 9. When I square the z minus 1, the square root of that, I get that. So this will be 9z minus 9. When I square the 2, I get 4. When I square the square root, I get rid of the square root. So this will turn into 8z plus 8. Now I'll bring the 8z over to the left by subtracting it from 9z. And I'll bring the 9 over to the right by adding it. I doubt that this is extraneous, but I should probably check. I have 3 times 17 minus 1. Is this equal to 2 times 17 is 34 plus 2? Well, this is 3 times the square root of 16, which is 3 times 4, which is 12. Is that equal to 2 times the square root of 36, which is 2 times 6, which is 12? So that works. So that's the answer. Okay, notice we have a square root is equal to k. So as long as k is at least 0 when I'm done, it's not going to be an extraneous root. If k is equal to some negative, then I'm going to have a square root is equal to a negative, and I got to throw that out. All right, so I'm going to square both sides. When I square the left, I get k squared. When I square the right, I get rid of the square root. And then I subtract k squared from each side. I'm going to move this negative 20 to the left to be a positive 20. And I'll divide each side by 4, so k is equal to 5. And again, I know that that's not going to be extraneous. I'm not going to bother checking it because this is 5 is a positive, and so that is going to work out. Okay, again, as long as when I'm done, x is at least 0 or positive, I'm not going to pick up an extraneous root because the square root has to be at least a 0 or, so if that turns into a negative, I got to throw it out. All right, so I'm going to square both sides. I'm going to subtract x squared from each side, and I'll move the 9 over by subtracting it. So x is equal to negative 3. But again, I know that x cannot be negative, so I have to throw this answer out, which leaves me with a no solution. The negative 3 was what we call an extraneous root. Okay, so I'm going to square each side. I've isolated the radical, so we don't need to do anything there. We square the left and get rid of the square root. we square up the right, which is a binomial. So the binomial is the first item squared, twice the product of the two items, and then the last item squared. Okay, I'm going to move these to the right-hand side to solve. So I'll have 0 is equal to x squared. When I move the negative 6 over by adding it, I get plus 7x. When I move the 9 over by subtracting it, I get 0. So now I'm going to put the 0 on the right because I prefer it there. I'll factor the common factor of x out, and I'll be left with x plus 7. So this tells me that x is equal to 0 from this one and negative 7 from this one. Now 0 works because 0 plus 3 is a positive number. But negative 7 has to be thrown out because negative 7 plus 3 is a negative 4, and that would cause the radical to be negative. So that's an extraneous root. So my only answer is x is equal to 0. That's the only valid answer. Okay, when I square the left, I get rid of the square root. When I square the right, that's a binomial. So remember, it's the first item squared twice the product of the two items, which is a 6, and then the last item squared. If you don't remember that shortcut, just write it out by foiling it. Okay, now my k squareds drop out from either side through subtraction. I'll move this k over here. So I'll have 6k minus 2k is 4k. I'll move this 9 over here to the left by subtracting it, and I'll get 0. So this tells me that k is equal to 0. And that's fine because a 0 plus a 3 is a positive number. So that's not going to give us an extraneous root. Okay, in this problem, when we find r has to be 0 or negative. If r is any positive value, that's going to make this a negative value. And that'll make the square root equal to a negative number. So r is okay as long as r is a negative number or 0. Okay, so let's square each side. I'll square the left and get that. I'll square the right and I'll get a positive r squared because anything squared is positive. Now I'll subtract r squared from each side, and I'll move this 3 over to the right by subtracting it. And 9r is equal to negative 3. And then I'll divide each side by 9, and I'll get r is equal to negative 3/9, which is negative 1/3. That's okay because it's a negative value, and a negative is a positive 1/3. And so that's not going to create an extraneous root or an extraneous solution. Okay, the first thing I want to do in this problem is isolate the radical, which means I have to move these terms to the other side. So I'm going to have the square root of z squared plus 12z minus 4 is equal to, when I move the negative z over, it becomes a positive z. When I move the positive 4 over, it becomes a negative 4. Now I'm going to square both sides. I square the left and I get z squared plus 12z minus 4, I just get rid of that, and I'll square this binomial, which is the first item squared, twice the product of the two items, and the last item squared. Again, if you don't remember that formula, just FOIL it out like that. That's a square, okay? And you'll get to that. All right, I'm going to subtract z squared on each side. I'll move this 8z over to the left by adding it. And I'll move this 4 to the right by adding it, and I'll get 20. So z is equal to 1. But be careful. Let's take a look at the last line before squaring. Now you can check at any point before you square. Once you square, this check is not going to work. It's easier to check here because you've isolated the radical. And a 1 minus a 4 is a negative 3. That makes the square root equal to a negative number. So this is an extraneous root and has to be thrown out. There's no other solutions here, so this problem is a no solution. Okay, here we have a cube root. You're never going to pick up extraneous roots when the index is odd. So you don't ever have to worry about that check. It's only when the index is even that you have to worry about extraneous roots. So here I'm going to cube each side and get 2x plus 5 on the left and 6x plus 1 on the right. I'll move this x to the right by subtracting it. I'll move the 1 to the left by subtracting it, and I'll get x is equal to 1. I know it's not extraneous, so I'm just going to move on. Okay, I'm going to start this problem by cubing each side. I cube the left and I get a squared plus 5a plus 1. I cube the right and I get a squared plus 4a. I subtract a squared from each side. I move my 4a to the left by subtracting it. 5a minus 4a is a. And I'll move my 1 to the right by subtracting it, and that's a negative 1. I don't have to worry about extraneous roots, so I'm done. Okay, I'm going to start by cubing each side. I cube the left and get that. I cube the right and get rid of the cube root. I move my m to the left by subtracting it. I move my 1 to the right by adding it, and I'm done. Okay, here my index is even, so I do have to worry about extraneous roots. I cannot have a solution that allows either of these values to become negative. So let's start by taking each side to the 4th power. And then I'll subtract a from each side, so I'll have 8 is equal to a, and that's not going to make either side negative, so we're done. So I'm going to start by isolating my radical, moving that over, and I have the cube root of x minus 8 is equal to negative 2. Now, this is a negative here on the right, but this is an odd index, so that's perfectly okay. That's not a problem at all. If it was an even index equal to a negative, we'd stop and say no solution. So now I'm going to cube each side. When I cube the left, I get x minus 8. When I cube the right, I get negative 8. And I'm going to add 8 to each side, so x is equal to 0, and I don't have to worry about extraneous solutions. Okay, I'm going to start by isolating the radical, moving the 4 over, so I have the 4th root of 2k minus 5 is equal to negative 4. And now I'm going to stop because I have an even index equal to a negative number. That's impossible, so this is a no solution, and I'm done. All right, this is a lengthy problem. When you have two radicals in the same problem, you're going to have to put one radical on each side of the equal sign. So I'm going to start by moving this over to the right. So I'll have root k plus 2. I should start writing a little small here. 1 plus root k plus 3. Now I'm going to square each side. When I square the left, that's super easy, k plus 2. When I square the right, I have a binomial. This 1 is my first term in it. This root k plus 3 is a second term in my binomial. Remember, the shortcut is the first item squared twice the product of the two items. The product of the two items is 1 times root k plus 3, so twice that is 2 times root k plus 3. And finally, the last item squared. This squared is just getting rid of the radical, so it's plus k plus 3. Now, notice what you did is you took an equation with two radicals and you simplified it down to one radical. So let's simplify by combining like terms. I have, let's see, 4k plus 4 plus 2k plus 3. Now I've got to isolate this term here because it has a radical. So I have to move this to the left by subtracting it, and that k minus k is 0. And I have to move this to the left by subtracting it. And I'll have 2 minus 4 is a negative 2. Oh my goodness, I wrote this radical wrong. Let me clean this up. I was going to get if I got a negative 2 on the left, I would have had to have stopped there and said no solution. But I realized that I had written this was a minus and somehow I magically changed it to a plus. So let me fix that. That's a minus. That's going to change this. That's a minus. that's going to change this. That k is a minus. And that's going to change this. Sorry for that confusion. That's going to become a minus. Oh, wait a minute. And 1 minus 3, this 4 is 1 minus 3, so that's going to become a negative 2. Oops, what did I just do? Okay, so now when I bring my k over, the k's drop out. And when I bring the 2 over, it becomes a 4. 2 plus 2 is 4. Equals 2 root k minus 3. And then I'm going to divide each side by 2 to keep my number smaller, because I can. So this is 2 and k minus 3. And finally, I'm going to square both sides. So I'll have 4 equals k minus 3. And when I add 3 to each side, I'm going to get 7 is equal to k. So my final answer is k is equal to 7. Sorry, I know that was super confusing because I had written that line wrong. Okay, here we go. We're going to separate the radicals, one on each side, by moving this over. And I'm going to end up with the square root of 2r plus 11 is equal to the square root of 5r plus 1 minus 1. And now I'm going to square both sides. When I square the left, I get 2r plus 11. When I square the right, this is a binomial. This is one term in the binomial. This is the second. So remember the shortcut. When you square a binomial, you square the first term. So I get rid of the square root. Then twice the product of the two. Oops, what happened? Twice the product of the two is like this. And then the last item squared. Negative 1 squared is plus 1. So if I combine like terms, I get 5r plus 2 minus 2 5r plus 1. Okay. Now, I'm going to move this radical to the left because I want it to be positive. So when I do that, I get a positive 2 root 5r plus 1 on the left, and then I'm going to move this to the right by subtracting it. 5r minus 2r is 3r, and I'll move this to the right by subtracting it. 2 minus 11 is negative 9. Now I'm going to square both sides to eliminate the final radical. When I square the left, I got to square this and get a 4. And I'll square this and get rid of the radical and get 5r plus 1, which is going to give me a 20r plus 4. When I square the right, I have a binomial. So remember, you square the first item, 9r squared, twice the product of the two items, so negative 54r, because the product of the two is negative 27, but twice that. And then the last item squared. Negative 9 squared is a positive 9. So let me bring this up here. I'm going to move my 20r to the right by subtracting it. And I'll have 9r squared. I'll move the 20r over by subtracting it, and I'll get negative 74r. And I'll move the 4 over by subtracting it, and 9 minus 4 is a positive 5. And this is equal to 0, because I moved everything to one side. The 0 is actually on the left, but I put it now on the right. Okay, so now, God, this is a really rough thing. So, oops, I made a mistake. My last item squared is 9 squared is not 9, it's 81. Sorry about that. You may have been wondering why I put the 9 there. That should be a plus 81. And then so when I bring my 4 over by subtracting it, 81 minus 4 is 77. So this is a plus 77. Oops. Okay. Let's see. This is rough to factor. I'm going to have, well, this is probably a negative 11 and a negative 7. So let me do that first. And remember, I'm trying to get to 74 through addition. So 33 and 21 won't do it. It's got to be a 9 and a 1. I got to just figure out where to put the 9. So if I put the 9 here, that gives me a 63 on the outside. And a 1 here gives me an 11 on the inside. And that adds up to 74. So this tells me that R is equal to a positive 11 over 9 and a positive 7. Now, both of these values may not be possible because remember, you can always pick up extraneous roots if you're not careful. So I have to go back to the place where before the first squaring in order to determine if I have an extraneous root. So I'm going to go back to this point in the equation right here. Or it doesn't matter. I could have gone back to the one above it. But if I have the square root of, now let's test the 11 over 9. 2r is 22 over 9 plus 11, which I'll write as 99 over 9. Is that equal to the square root of 5r, which is 5 times that is 55 over 9, plus 1, which I'll write as 9 over 9, minus 1. Is this true? Well, up on top on this one, I have 121 over 9. Let me move this up. Oops, I have some weird work over here. Okay, I don't know where that came from. All right, so this is it equal to the square root of 55 plus 9 is 64 over 9 minus 1. Well, this is 11 over 3. Is this equal to 8 over 3 minus, and I'll put 1 as 3 over 3? The answer is no. That doesn't work. 11 over 3 does not equal to 5 over 3. Therefore, this was an extraneous root. Now let's test the 7. When I test the 7, I'll have the square root of 2r, which is 14. I'm just looking at this equation right here. Plus 11. Is this equal to the square root of 5r, which is 35, plus 1, minus 1? Well, this is the square root of 25. The square root of 36 minus 1. So this is 5 equals 6 minus 1, and that's true. So x does equal 7. So that's my one and only answer. That was a lot of work. Okay, so I'm going to separate my radicals in order to start. I'll move that to the right, and I got to write small so I can fit it on this page. But 3p plus 4 is going to be equal to a positive 2p minus 4 plus 2. Now I'm going to square both sides. When I square the left, I just get rid of the radical, the square root. When I square the right, I have a binomial. Remember, this is the first term, that's the second term. So when you square a binomial, it's the square of the first term, so it just gets rid of the square root, twice the product of the two, and then the square of the last. So let me clean this up a little bit on the right by combining like terms. I get 2p, the negative 4's go away, so I have just this. Okay? On the left, I have this. So now I took a problem where we had two radicals, and I boiled it down to something with just one radical. And now I'm going to repeat this process to get rid of the final radical. So I'm going to start by moving the 2p to the left by subtracting it, because I want to isolate my radical. 3p minus 2p is p. I'll move, actually that's it, there's nothing else to move. So I have this plus 4 is equal to 4 root 2p minus 4. Okay, when I square the left, I'm squaring the binomial. So I have the first item squared, twice the product of the two items, and the last item squared. When I square the right-hand side, I got to square each part. So when I square the 4, I get 16. When I square the square root, I get rid of the square root. So this is going to become 32p minus 64. Now this is a quadratic equation because I have a variable that's being squared. So to solve this, I need to set it equal to 0. So I'm going to bring my 32p to the left by subtracting it. And I'll get 8 minus 32p is negative 24p. And I'll bring my 64 to the right by adding it. And I'll get 16 plus 64 is a positive 80. And now this is equal to 0. So let me bring this up here to continue. I'm going to factor this to solve. So I have, it looks like I have I'm trying to get to negative 24 through subtraction, through addition. So negative 20 and negative 4. That multiplies to 80 and adds up to 24. So this tells me that p is equal to 20 and 4. But we have to check our answers because these may not be valid answers. So I got to double check it. Now let's check that p is equal to 20. I'll just put it into the original. The square root of 3p, which is 60, plus 4, minus, I'm just plugging it in right here. The square root of 2p, which is 40, minus 4, is this really equal to 2? Well, the square root of 64 minus the square root of 36, is that equal to 2? 8 minus 6 equals 2. That checks out. So 20 is valid. Let's check the 4. I'm going to plug it in again. The square root of 3p, which is now 12, plus 4, minus the square root of 2p, which is 8, minus 4. Is this equal to 2? Well, the square root of 16 minus the square root of 4, is this 2? Well, 4 minus 2, this is equal to 2. So that works out. So that checks out. So both of these are valid solutions. Neither of them are extraneous, and they both have to be included. Okay, in this problem, we've already separated the radicals, so I'm ready to square each side. When I square the left, I have a binomial. So this is my first term, that's the second term. So the shortcut is the square of the first term, which is just getting rid of the square root, twice the product of the two, and then the square of the last. So that's the squaring of the left-hand side. When I square the right-hand side, I just get rid of the square root. Okay, so let me clean this up a tiny bit. This is going to be 3 plus 9 is 12 minus 3p minus 6 root 3 minus 3p. Equals 3p plus 2. Now, I want to move my radical to the side that's going to be positive. I don't want to deal with a negative radical. So I'm going to move this over to the right. So on my equal sign, I'll have positive 6 root 3 minus p. 3 minus 3p. Okay. I'm going to move this to the left. So I have a negative 3p on the left. I move this again and I get negative 6p. Because negative 3p minus 3p is negative 6p. And then I move this 2 to the left by subtracting it, and I have 12 minus 2 is 10. Okay, you don't have to do this, but I'm going to do this to keep my numbers smaller. I'm going to divide everything by 2. It just keeps my work a little bit smaller before I square each side to get rid of that radical. So when I square the left, I have a binomial. So I'm going to square the binomial, which is the first item squared, twice the product of the two items. So the product of the two items is negative 15p. Double that is 30p. And the last item squared. Okay. When I square the right-hand side, I have to square each of these parts. So when I square the 3, I get 9. When I square the square root, I get rid of the square root. So this is going to be 27 minus 27p. Now this is a quadratic equation, so I got to move these to the left. So let's bring this up here. On the right, I have a 9p squared. I'll write that first. And then I bring my 27 over by adding it to the negative 30 that's already there. Negative 30 plus 27 is negative 3p. And then I bring my 27 over by subtracting it from the 25 that's already there. 25 minus 27 is negative 2. And now this is equal to 0. So I'll factor this. Okay, I know that this is 2 and this is 1. That's the only way to get to 2. I'm trying to get to 3 through subtraction. So it looks like I have to have a 3p and a 3p. Putting a negative here gives me a negative 6p on the inside, and a plus here gives me a plus 3p on the outside. So this tells me that p is equal to a positive 2/3 and a negative 1/3. All right, now unfortunately I'm not done yet because I have to check. So let's check the 2/3. I'm plugging this into the original now. Okay, so I have the square root of 3 minus 3p. Well, 3 times this is 2 because the 3's cancel. Minus 3, is this really equal to 3p? Well, 3 times that is 2 plus 2. 1 minus 3, is this equal to the square root of 4? No, this is negative 2 is equal to 2. That's not true. So this has to be thrown out, and that cannot be part of our solution. Let's check the p when p is equal to negative 1/3. Okay, when p is equal to negative 1/3, I have the square root of 3 minus 3 times this, which is a plus 1. Negative 3 times negative 1/3 is a positive 1. Minus 3, is this really equal to the square root of 3p? Well, 3 times this is negative 1 plus 2. I'm going to move this up a little bit. So here I have the square root of 4 minus 3. Is this really equal to the square root of 1? This is 2 minus 3 is equal to 1. That's also not true. This is negative 1 is equal to 1. So this is not a possible answer either and has to be thrown out. Now both of my possible answers have been thrown out and I don't have a valid answer, so this is no solution. Okay, so I'm going to write this like this so that it's a little more recognizable. This is 2x minus 9 square rooted equals 2 plus the square root of x minus 8. That's what to the 1/2 power is, a square root. Okay, so now I'm going to square the left-hand side, which is going to give us 2x minus 9. I'll square the right-hand side, and this is a binomial. Oops. This is a binomial. So when I square the first item, I get 4. Twice the product of the two items is 4 times x minus 8. And the square of the last item is simply x minus 8. And this is going to simplify to x minus 4 plus 4x minus 8. That's just combining the like terms. Okay, now I'm going to move my x over to the left by subtracting it, and I'll get x. I'll move my 4 over to the left by adding it, and I'll get negative 5. So now I'm going to square both sides. When I square the left, I'm squaring this binomial. So I get x squared minus 10x plus 25. When I square the right, I got to square this, which is 16, and then I square this, which is x minus 8. So I get 16x minus 128. Now this is a quadratic equation, so I gotta set it equal to 0. So I'm gonna bring the 16x over. So I'll get x squared, negative 10 minus 16 is negative 26x, and I'll bring the negative 128 over by adding it, and I'll get a positive 153. Okay. So I'm going to factor this. Now this is a tough one to factor, but I know that they're minus and minus, and I'm trying to add up to get to 26. Well, let's take a look at 153. 153 is divisible by 3, and this is going to be 51. This is 3 times 17. So that looks like it's going to be a minus 9 minus 17. And that adds up to 26 and multiplies to a positive 153. Okay, so now this gives me that x is equal to 9 and positive 17. But I've got to double check both of those answers. It feels like this never ends. So I'm going to check the x equals 9, and I'm going to plug it in right here. So the square root of 18 minus 9, is this equal to 2 plus the square root of 9 minus 1? Well, this is the square root of 9 equals 2 plus the square root of, I put 1 here, but this is an 8. So this is the square root of 1. So is it 3 is equal to 2 plus 1? That's true. So x is equal to 9. Now let's check if x is equal to 17. Well, the square, and I'm plugging it in right here. The square root of 2x is 34 minus 9. Is this equal to 2 plus the square root of 17 minus 8? Okay, so let's move this up so I give myself a little more room. And I'm going to continue. This is the square root of 25. Is this equal to 2 plus the square root of 9? Well, is 5 equal to 2 plus 3? It is. So this is a valid answer. So both of these are valid, and that's my entire solution. Okay, when we solve this, I'm going to square both sides, and I'll get v squared is equal to 2k over m. And then I'm going to multiply each side by m. So v squared times m is equal to 2k. And I'll divide each side by 2. So v squared m over 2 is equal to k. And we're done. Okay, we'll start this problem the same way by squaring each side. So I'll get v squared is equal to 2k over m. I'll clear the fractions by multiplying each side by m. So v squared m is equal to 2k. But this time I'm after this m, so I'll divide each side by v squared. And I'll get m is equal to 2k over v squared. Okay, we're solving for L. I'm going to start by squaring each side to get rid of the square root. I'll clear my fractions. by multiplying each side by c, and we're done. Okay, I'm going to clear my fraction by multiplying each side by the denominator. So I'll put this in an order that makes sense. I'll put 2 pi f root LC, although it didn't matter too much what order you put that in. That's equal to 1. And then I'm going to square both sides. So I'll have 4 pi squared f squared LC is equal to 1 squared, which is 1. And finally, I want to solve for L, so I'm going to divide everything else away. So L will be equal to 1 over 4 pi squared f squared c. And that's all you can do. So you're done there. Okay, so I'm going to square each side to clear the square root. I'll multiply each side by f to clear the fraction. And I'll divide each side by r squared to solve for f. And we're done.